Okay, in the last lecture, we had drawn the voltage transfer characteristic of the CMOS inverter, and we had identified the different segments in that voltage transfer characteristic. We had a total of 5 segments within that voltage transfer characteristic. So let me draw the CMOS inverter once again. So first, we have the supply voltage, that is what VAD, and then the pull-up network, which contains only one PMOS transistor, and then the pull-down network, which contains the NMOS transistor, and then ground. Both the gates are shorted together, that is where the input is applied, and both the drains are also shorted together, and that is where the output is taken. And for this CMOS inverter, we had the following voltage transfer characteristic, which is something of this sort, yes or no? So as the value of Vn is varied from 0 to VAD, the value of V0 will gradually decrease from VAD to what? 0, yes. In fact, this value is what? VDD. And in fact, if you recall, the value of Vn where the curve or the VTC would touch down on the x-axis, it is what? VAD minus mod VTP. It is what? VAD minus mod VTP. So this is what the complete voltage transfer characteristic of any CMOS inverter. Okay, now that we have the voltage transfer characteristic of the CMOS inverter, what I'll do, I'll take a resistor and connect it between the input and output terminals of the CMOS inverter or the NOT gate. Okay, look at this. I'll just connect a resistance between the input and output of the CMOS inverter. Let me call this resistance as what? Some RG. Here it is important to understand that for the CMOS inverter, we are not applying any input voltage, node voltage. When I say Vn, it is just the name of the node voltage, and also V0 is what? Name of the node voltage. At which node? At this node. Vn is what? Name of the voltage at this node. You understood? So for this CMOS inverter, the only thing we are connecting is what? A resistance between input and output terminals. We are not applying any input voltage as such. Okay. Now when you connect this resistance RG between input and output, remember for any MOSFET, the current flowing at the gate, it is what? 0. So this current, it is what? 0. This current is also 0. And because these two currents are what? 0. Because these two currents are 0, even the current through RG from KCL would it not be 0? Now because the current through RG is what? 0, the voltage drop across RG is also going to be 0. And since RG is what? Between input and output, can we not say V0 becomes equal to Vn, or the output voltage becomes equal to the input voltage upon connecting this resistance between the input and output of the CMOS inverter or the NOT gate. Okay. So here what is happening? Because of RG, V0, it becomes equal to what? Vn. Now what is this V0 equal to Vn? Is it not y equal to x, which is a straight line passing through origin with a slope 1? So on this plot between V0 and Vn, we have one more relationship to plot, which is what? V0 equal to Vn. Like I said, it will be a straight line which will pass through origin and which has a slope of 1. Okay. So if you take any point on this straight line, always the x coordinate will be equal to what? Y coordinate, since y is equal to x or V0 equal to Vn. So if I ask you, what is the operating point of this CMOS inverter? Is it not the point of intersection between these two curves? One is what? The voltage transfer characteristic of the CMOS inverter. And since you connect this RG between input and output, you get this additional line, which is called the load line. Okay. And the point of intersection, is it not this thing? And this point of intersection will have an x coordinate, that is what? The value of Vn, and also a corresponding y coordinate, which is the value of V0. But since the point of intersection lies on the line V0 equal to Vn or y equal to x, the x coordinate or the value of Vn and the y coordinate or the value of V0 both are going to be identical, V0 equal to Vn. Now the question is, what is the point of intersection? What is the point of intersection? So right now we know one thing, that is what? V0 equal to Vn. V0, is it not the drain voltage for both the transistors? Yes or no? V0 is what? Drain voltage for both the transistors. Whereas Vn, is it not the gate voltage for both the transistors? And right now V0 is equal to what? Vn. And since V0 is equal to what? Vn, is it not like for both the transistors, the drain and the gate are at same potential? If the drain and gate are at same potential, does it not mean both are operating in saturation? So when you connect this RG between input and output of the NOT gate, then both the transistors will operate in saturation, since for both the transistors, the drain voltage is equal to gate voltage. And why is that? Because the current through RG is what? 0. So the voltage drop across RG is also going to be 0. I hope it is clear, okay? So look at this operating point. In which segment does it lie on the voltage transfer characteristic? Remember, in the voltage transfer characteristic, there are segments, okay? This is what? First segment. This is what? Second segment. This one is what? Third segment. Then this is what? Fourth segment. This one is what? Fifth segment. In the first segment, NMOS is off, PMOS will be in deep triode. In the second segment, NMOS turns on in saturation and PMOS will operate in triode. In the third segment, both will operate in saturation. And right now also, since drain and gate are at same potential for both the transistors, the operating point, it will definitely lie in the third segment, and that is where both NMOS and PMOS are going to operate in saturation. And there is also the high slope or high negative slope region of the voltage transfer characteristic, because if both are in saturation, it is like having two common source amplifiers, and any common source amplifier will have a large negative gain. And two common source amplifiers, it means what? We have an even larger negative gain. That is why the large negative slope or the high negative slope region, and that is what? The third segment of the voltage transfer characteristic. And then in the fourth segment of the voltage transfer characteristic, NMOS will go into what? Triode, whereas PMOS, it remains in saturation. And it is in the fifth segment that the PMOS transistor, it turns off, and NMOS remains in deep triode. Anyway, the point is what? Right now, when you connect this RG, both the transistors are going to be in saturation, and the operating point, it is somewhere in the third segment of the voltage transfer characteristic, where we have a large negative gain, okay? What is the name of this current? Is it not the current flowing through PMOS? Let us call this as what? IP. What is this current? Is it not the current flowing through NMOS? And let this current be IN, okay? Now again, look at the output node. At the output node, how many currents are flowing? Actually 3 currents are flowing, but then this current is what? 0. So only 2 currents are flowing, and which are IP and IN. IP is what? Entering, IN is what? Leaving. Obviously, IP should be equal to what? IN, okay? So here, IP must be equal to IN. So the value of V0, which is same as the value of Vn, will be such that IP will be equal to what? IN, and both the transistors are operating in saturation. Just write down the equations for IP and IN, equate both the currents, you can easily solve for V0, and that is what is the operating point of this CMOS inverter when a resistance is connected between input and output terminals, so that V0 becomes equal to Vn, okay? And let that operating point be Vm, okay? So when you equate IP and IN and solve for V0, let the value of V0 that results be denoted by Vm, and this Vm is known as what? The switching threshold of the inverter, okay? So what is it? It is called the switching threshold of the inverter. So V0 equal to Vm, it also means what? Vn is also Vm, because after all, V0 is equal to Vn. So just tell me, what are the x and y coordinates of this point of intersection between the VTC and the straight line V0 equal to Vn? is it not? Vm comma Vm. Vin is what? Vm. V0 is also Vm. Now, for any inverter, you can always find the value of the switching threshold just by connecting a resistance between input and output terminals. Of course, you have to connect the power supply. And knowing the value of Vm, that is what the switching threshold of a CMOS inverter, will convey a lot of useful information about the NOT gate, and we'll find out what that information is. Okay, before that, we'll deviate a bit and look at the notion of the strength of a MOSFET or the strength of a transistor. Okay, so what is that? Strength of the transistor. Okay, so in very simple words, when we say strength of a transistor, it only means what? The current driving capability of that transistor. Okay, so strength of a transistor will refer to what? The current driving capability. Current driving capability of the transistor. Now, for any transistor, in what region of operation the drain current is going to be maximum for a given value of VGS? Look at this. So, VGS is what? Fixed. VGS is what? Fixed. And this fixed value of VGS will obviously be greater than VTH. Only then current will flow through the transistor and so on. So, in brackets, I'll write VGS is greater than VTH, meaning the transistor, it is going to be on. Okay. And if VGS is what? Fixed, does it not mean the overdrive voltage? What is this overdrive voltage? Is it not VGS minus VTH? Yes. And what does this overdrive voltage decide? It will decide the number of electrons in the N channel or the number of holes in the P channel. Okay. And the number of electrons in the N channel will decide the conductivity of the N channel, which in turn will decide the resistance of the N channel and so on. Okay. So when VGS is what? Fixed, VGS minus VTH is also going to be fixed. So for a given value of overdrive voltage, that is what? VGS minus VTH, in which region of operation the drain current is going to be maximum. Is it not in saturation? Again, if you go back to the plot between ID and VDS, if you go back to the plot between ID and VDS, what was the plot like? Was it not something like this? So as long as it is in triode, and what is that value of VDS which is at the boundary between triode and saturation? It is VGS minus VTH. So when VDS is what? Less than VGS minus VTH, the MOSFET, it operates in triode. And when VDS is what? Greater than VGS minus VTH, the same MOSFET goes into saturation. And usually in saturation, the drain current becomes constant or independent of VDS, like this. Okay. And here, obviously, we are ignoring channel length modulation. If there is a channel length modulation, you know the drain current will be proportional to VDS in saturation. So instead of being constant and independent of VDS, it will linearly increase with VDS. Okay. So this white color stuff is what? Without channel length modulation, and this yellow color linear dependence of ID on VDS is what? It is with channel length modulation and so on. Okay. And my original question is what? In which region of operation the drain current is going to be maximum for a fixed value of VGS minus VTH? Is it not in saturation? Because in triode, the value of drain current is what? Like this, and like this. Whereas in saturation, the drain current is what? This thing. And that drain current is what? ID sat. So now the conclusion is what? For a fixed value of VGS minus VTH, the drain current is going to be maximum in saturation. For a given value of VGS minus VTH or VGS, the drain current is going to be maximum in saturation. Okay. ID is what? Maximum in saturation. As you can see, from the plot between ID and VDS. Okay. Now let us again get back to the notion of the strength of a transistor, which is same as what the current driving capability of the transistor. Okay. So let us say we have two transistors. Initially, let both the transistors be NMOS. Look at this. Let this be M1, let this be M2, let the current for M1 be I1, and let the drain current of M2 be I2, and look at how they are connected. Are they not connected in parallel? Both the gates are shorted together, and both the sources are shorted to ground. Gates at same potential, sources also at same potential. M1 and M2 both are in parallel, okay? And between gate and ground, let me connect a voltage source. Can I call this voltage source as VGS? Because the value of this voltage source is nothing but the voltage drop between gate and source for both the transistors, okay? So let this be VGS. So here the point is what? VGS1 is equal to VGS2 is equal to what? The value of this voltage source, which is VGS. And let me also say that for both M1 and M2, the threshold voltage, it is what? Same, okay? VTH1 equal to VTH2 equal to what? VTH. Now if VGS is what? Same for both transistors, and if VTH is also same for both transistors, can I not say VGS1 minus VTH1, which is what? The overdrive voltage of M1 is same as the overdrive voltage of M2, which is VGS2 minus VTH2, and these two will be equal to what? Since VGS1 and VGS2 are equal to what? VGS, and VTH1 and VTH2 are equal to what? VTH. The two overdrive voltages can be written as what? VGS minus VTH. VGS minus VTH. And usually the value of mu and Cox will be same for all transistors in any given technology, okay? So mu and Cox is what? Usually same for all NMOS transistors in any given technology, okay? Later on you'll understand what is the meaning of in a given technology, okay? But for now, just take it granted from me that mu and Cox will be what? Usually same for all transistors in any given technology, okay? But the aspect ratio of the different NMOS transistors in a given technology need not be same. So as a circuit designer, you don't have control over mu and Cox, but you have control over what? The values of W and L or the aspect ratio itself, okay? So W by L, it is in the control or the discretion of the circuit designer, okay? And let us say the W by L ratio of M1 is what? 4 times W by L ratio of M2, okay? Look at this. W by L1 is what? 4 times W by L2. W by L1 is what? 4 times W by L2. Now, when will both the transistors carry maximum current? When both are operating in saturation. So let us say M1 and M2 both are in saturation so as to carry maximum current and so on, okay? And in saturation, what is the current equation or the drain current equation ignoring channel length modulation? Is it not half mu and Cox W by L then square of the overdrive voltage? So I1 will be equal to what? Half mu and Cox W by L of M1, which is W by L1 times VGS1 minus VTH1 whole square, and that is same as what? VGS minus VTH whole square, okay? VGS minus VTH whole square. And similarly, I2 is what? Half mu and Cox W by L2 times VGS minus VTH whole square. Now if you divide the two equations, left hand side will be what? I1 divided by I2. Now on the right hand side, a lot of factors are common, yes. First of all, half mu and Cox, both will cancel out. Since the two transistors are in parallel, they'll have the same overdrive voltage. Even the overdrive voltage factors will cancel out. What is left? W by L1 divided by W by L2. And I have already told you that W by L1 is what? 4 times the other aspect ratio. So when you divide these two, right hand side, would it not be 4? That means what? I1 equal to 4 times I2. I1 equal to 4 times I2. So are the two transistors having the same overdrive voltage? Yes. But do the two transistors carry the same current? No. I1 is what? 4 times I2. So is it not like this? For the same overdrive voltage, M1 carries 4 times as much current as M2? Yes or no? For the same overdrive voltage, M1 carries 4 times as much current as M2 does. So M1 is what? 4 times stronger than M2. I hope the notion of strength is clear. For the same overdrive voltage, if one transistor carries more current than another transistor, then the first transistor is what? Stronger than the second transistor. Okay, and here for the same overdrive voltage, I1 is what? 4 times I2. So I can say that M1 is what? 4 times stronger than M2. Because I1 is what? 4 times I2. Had W by L2 been 4 times W by L1, then you will have to say M2 is what? 4 times stronger than M1. Okay? So the strength of the transistor, is it not directly proportional to that mu and Cox W by L, which will multiply the square of the overdrive voltage? Yes. So strength of the transistor is directly proportional to mu and Cox W by L. And this mu and Cox W by L is also referred to as what? Beta. Just some notation. So strength of the transistor, that is what? The current driving capability, is directly proportional to mu and Cox W by L if it is what? NMOS. And if it is PMOS, then it will be directly proportional to mu P Cox W by L. So depending on whether it is NMOS or PMOS, it can be proportional to either mu and Cox W by L or mu P Cox W by L. And this mu P Cox W by L will be referred to as what? Beta P, whereas this one will be referred to as what? Beta N. You understood? Yes. Now, there is also one more way to look at this. Once again, let's say there are two transistors, M1 and M2. And this time, let both the transistors carry the same current in saturation. Okay. So I1 is what? I. I2 is also the same I. Okay. And let this be VGS1 and let this be VGS2 and so on. Okay. And once again, M1 is what? 4 times stronger than M2. Okay. So let us say M1 is what? 4 times stronger than M2. M1 is what? 4 times stronger than M2. It means what? For the same overdrive voltage, M1 will carry 4 times as much current as M2 does. Okay. But this time both the currents are what? Equal. Just tell me between VGS1 and VGS2, which one would be higher given that they have the same threshold voltage. Just think and answer. Here we have two transistors which are not identical. Identical means what? Having the same strength. Having the same strength, it means what? Mu Cox W by L has to be same for both transistors. Okay, but here I am saying what? M1 is 4 times stronger than M2, and that both the drain currents are equal, or both the transistors are carrying the same current. And the question is what? For which transistor the gate to source voltage is going to be higher? Is it for the stronger transistor or is it for the weaker transistor? You see, the drain current ID is a product of two factors, okay. One is what? The strength of the transistor, which is directly dependent on mu n Cox and then W by L. And the second is what? The square of the overdrive voltage, okay. VGS minus VTH whole square, okay. So here, as you can see, we have two factors. One is what? The strength of the transistor, which is mu n Cox W by L. Second is what? The square of the overdrive voltage, which is VGS minus VTH whole square. And here, in this particular scenario, even though both the transistors are not identical and so on, they still have the same current, which means what? ID is what? Same for both transistors. Same for both transistors. Now this mu n Cox, is it greater for M1 or is it greater for M2? M1 4 times stronger than M2. It means what? Mu n Cox W by L of M1 is what? 4 times that of M2. So this one is what? Greater for M1. This one is what? Greater for M1. Now the thing is what? This VGS minus VTH, will it be greater for M1 or greater for M2? And the constraint is what? That the product of these two factors is what? Same for both transistors, because already this factor is what? Greater for M1, and for the product to be same for both transistors, the other factor, that is what? VGS minus VTH whole square, should it not be greater for M2? Because if this thing is also greater for M1, both the factors greater for M1, even ID will be what? Greater for M1, but here ID is what? Same for both transistors. So obviously the other factor has to be greater for the weaker transistor, that is what? M2, okay. So VGS minus VTH, it will be greater for the weaker transistor, and in this case it is M2 that is weaker than M1. So again the conclusion is what? For the same current in saturation, for the same drain current in saturation, the weaker transistor requires a greater overdrive voltage. I'll say it again. For the same drain current in saturation, the weaker transistor requires a greater overdrive voltage, or you can also say the stronger transistor requires a smaller gate to source voltage or the gate overdrive voltage for the same drain current, okay. So what is it? Weaker transistor requires a larger overdrive voltage for the same drain current, that is what? ID in what region? In saturation. Earlier, what was the conclusion? For the same overdrive voltage, the stronger transistor will carry more drain current in saturation. And this time the conclusion is what? For the same drain current in saturation, the stronger transistor requires a smaller overdrive voltage, or the weaker transistor requires a larger overdrive voltage. Both are simple yet important conclusions. Now let us get back to the concept of the switching threshold of a CMOS inverter, which is the operating point when a resistance is connected between input and output of the CMOS inverter, okay. Okay, just have a look at these three cases. In the first case, mu n Cox W by L of NMOS is same as what? Mu p Cox W by L of PMOS. Does it not mean both the NMOS and PMOS are equally strong? Yes. In other words, beta n is equal to what? Beta p. This means NMOS and PMOS both are equally strong, or I can say both are matched. Equal strength, it means what? Both are matched, okay. And then look at the second case. Mu n Cox W by L of NMOS is what? 4 times that of PMOS. So this time, is it not this thing? Beta n is equal to what? 4 times beta p. And this means what? The NMOS is 4 times stronger than PMOS, okay. NMOS is what? 4 times stronger than PMOS. And look at the fourth case, 4 times mu n Cox W by L of n mass is what? Mu p Cox W by L of p mass. So is it not like this? Beta p is what? 4 times beta n. Beta p is what? 4 times beta n. And in this case, we can say p mass is what? 4 times stronger than n mass, okay? So this time, I can say p mass is what? 4 times stronger than n mass. Well, I hope now the notion of one transistor being relatively stronger or weaker compared to another transistor is clear, okay? So once again, we have the CMOS inverter for which a resistance is connected between input and output. And when you connect this resistance, because the current through resistance is what? 0, V0 becomes equal to Vin, and the operating point is known as what? The switching threshold, denoted by Vm. So in this particular connection, we're going to have output and input to be identical and equal to what? Some Vm, and this Vm is called the switching threshold and so on, okay? And then there are 3 different cases. In the first case, beta n equal to beta p, it means what? Both the n mass and p mass are equally strong, or they are what? Matched. In the second case, beta n equal to what? 4 times beta p. N mass is what? 4 times stronger than p mass. In the third case, beta p is what? 4 times beta n, which means p mass is what? 4 times stronger than n mass. And in each and every case, you have to find the value of the switching threshold of the CMOS inverter. That is what? The value of Vm. And also the value of the supply voltage and the threshold voltage of both the transistors are given. VDD is what? 5 volts. So in place of VDD, I can write down 5 volts. And VTN is what? Threshold voltage of NMOS. It is positive and equal to what? 1 volt. Whereas minus VTP is what? 1. Minus VTP equal to 1 is same as what? VTP equal to minus 1. If VTP is what? Minus 1, does it not mean mod VTP is equal to plus 1? Yes. So minus VTP equal to 1 is same as what? Mod VTP equal to 1. Let's find out Vm in each and every case. First case is what? Beta n equal to beta p. Again, beta n equal to beta p, it means what? Mu n Cox W by L of n mass is same as what? Mu p Cox W by L of p mass, okay? Look at this. First case. First of all, V0 equal to Vn equal to what? Vm. And this current, as you already know, is what? Ip. And this current is what? In. And at the output node, Ip is what? Entering, In is what? Leaving. You just have to equate the two currents. So Ip must be equated to what? In, okay? Well, before that, what is this voltage drop? Is it not the drop between source and gate of the PMOS transistor, which is VSGP? And what about this voltage drop? Is it not the drop between gate and source of the NMOS transistor, which is VGSN? And here, V0 and Vn both are equal to what? Vm. So look at VSGP. Is it not VED, which is what? 5 minus Vm? So V0 is what? Vm. Vn is also Vm. So VSGP is what? Plus 2 VDD minus 2 Vm. It is what? VED minus Vm, or 5 minus Vm for the given value of VED, okay? So in place of Ip, I can write down half mu p Cox W by L of PMOS, and that mu p Cox W by L of PMOS is what? The strength of the PMOS transistor, which is also denoted by beta p. So half beta p, and then square of the overdrive voltage. Why? Because both NMOS and PMOS are going to operate in saturation, since drain and gate are going to be at the same potential, okay? So half beta p into VSGP minus mod VTP whole square, and that should be equal to what? In. Since again NMOS is also operating in saturation, In, would it not be given by half beta n, which is mu n Cox W by L of NMOS times VGSN minus VTN whole square. And in the first case, beta n equal to what? Beta p. If beta n is equal to beta p, half beta n, both will cancel out. Now what is VSGP? VSGP is what? Like I already said, it is 5 minus Vm. 5 minus Vm minus mod VTP is what? 1 whole square is equal to VGSN minus VTN whole square. VGSN, look at VGSN in the circuit, plus to what? Vm minus to what? 0. So VGSN is what? Vm. So VGSN minus VTN is what? Vm minus 1 whole square, okay? Vm minus 1 whole square. Now you take square root on both the sides, you will get 4 minus Vm equal to what? Vm minus 1, or 2Vm equal to what? 5, and Vm is what? 5 by 2, and remember 5 volts is also what? VED. So I can say Vm when both the transistors are matched or equally strong is what? VED by 2, and in this case it is what? 2.5 volts, okay? So Vm, it is what? VED by 2, which is 2.5 volts. Is it clear? That is the first case. Let us also find the value of Vm in the second and the third cases, okay? See, whatever be the relative strength of the two transistors, the moment you connect RG between input and output, V0 becomes equal to what? Vin, and the two transistors are driven into saturation. So IP is always given by the same expression. Even IN will be given by the same expression. So the region of operation of the two transistors has nothing to do with the relative strength of the two transistors. As long as there is RG between input and output, both the transistors will remain in saturation. And in this case, that is what? The second case. So right now we are doing it for the second case where beta n is what? 4 times beta p, which means NMOS is what? 4 times stronger than PMOS, okay? Once again, all you have to do is to just equate IP and IN and find the value of Vm. Okay, you can easily do that. But without even solving this equation for the value of Vm, can you take a guess whether the value of Vm will be VED by 2 or less than VED by 2 or greater than VED by 2? Just from the fact that NMOS is what? 4 times stronger than PMOS, can you decide whether Vm in this case will be greater than VED by 2 or less than VED by 2? Think about it, okay? See, one thing that is always going to be true is what? IP should be equal to IN. Yes, an IP must be equal to IN, and that both the transistors are operating in saturation. So when the drain current is what? Same for both transistors that are operating in saturation, the overdrive voltage, will it not be greater for the weaker transistor? And in the second case, NMOS is what? 4 times stronger than PMOS. So NMOS is what? The stronger transistor, and PMOS is what? The weaker transistor. And just now I told you what? For the same drain current, the weaker transistor is going to have a greater overdrive voltage. Now, which is the weaker transistor in this case? PMOS is what? Weaker. Yes or no? PMOS is what? The weaker transistor. And for the weaker transistor, the overdrive voltage is going to be greater, okay? Now, for the PMOS transistor, that is what? The weaker transistor, what is the overdrive voltage? Is it not VSGP minus mod VTP? So definitely VSGP minus mod VTP, that is what? The overdrive voltage of the PMOS transistor, which is the weaker transistor, will be greater than that of the NMOS transistor. Now for the NMOS transistor, what is that overdrive voltage? Is it not VGSN minus VTN? So they should be greater than VGSN minus VTN. And for the values that are given for this circuit, VTN and mod VTP both are identical and equal to what? 1. So on both the sides, minus mod VTP minus VTN both will cancel out. Now again, come back to the circuit. What is VSGP? Is it not VDD minus Vm? VSGP is what? VDD minus Vm. It should be greater than VGSN. Look at VGSN plus 2Vm minus what? Ground. So VGSN, is it not just Vm? So right hand side is what? Vm. Minus Vm goes to the other side. 2Vm is less than VED. So Vm is less than VED by 2 or less than 2.5 volts, okay? So when the NMOS is what? Stronger than PMOS, then the switching threshold will be less than VDD by 2. Switching threshold is what? Less than VDD by 2, because the NMOS transistor will require a smaller overdrive voltage, whereas the PMOS transistor requires a larger overdrive voltage. You understood? Yes. Okay, now that we know what to expect, what is that? That the value of Vm is definitely going to be less than VDD by 2 or 2.5 volts. Now let's find out the actual value of Vm itself. Okay, once again, we have the same equation from Ip equal to what? In. Half will cancel out, because beta n is what? 4 times beta p. Beta p, beta n also will cancel out, and on the right hand side 4 will remain. Okay, once again, in place of VSGP, let me write 5 minus Vm minus mod VTP is what? 1 whole square is equal to what? 4 times VGSN is what? Vm minus Vtn is what? Minus 1 whole square. That's all. Take square root on both the sides. You will get 4 minus Vm is what? 2 times Vm minus 1. Again, 4 minus Vm is what? 2 Vm minus 2. So 3 Vm equal to what? 6, or Vm equal to what? 2 volts. As we expect, it is what? Less than VDD by 2 or 2.5 volts. So let me write down the value of Vm in the table. For the second case where NMOS is 4 times stronger than PMOS, the value of Vm, it is what? 2 volts. So what do you expect for the third case where PMOS is 4 times stronger than NMOS? Don't you expect that Vm is going to be greater than VDD by 2 or 2.5 volts? Okay. So in the third case, beta p is what? 4 times beta n. Once again, we have the same equation from Ip equal to what? In. On both the sides, half and half will cancel out. And because beta p is what? 4 times beta n, beta p, beta n will cancel out. This time on the left hand side, you're going to have 4. Okay. So what is it? 4 times VSGP is what? 5 minus Vm minus mod VTP is what? Minus 1 whole square is equal to Vm minus 1 whole square. Once again, take square root on both the sides. You will get 2 times 4 minus Vm is equal to Vm minus 1. 8 minus 2 Vm is equal to Vm minus 1. And this is same as what? 3 Vm equal to 9. And Vm, it is what? 3 volts, which is greater than VDD by 2. So in the third case, when PMOS is what? 4 times stronger than NMOS, value of Vm, it is what? 3 volts. So only when both the transistors are equally strong or matched, the switching threshold is equal to what? Half of the supply voltage, that is what? VDD by 2. And if the NMOS is what? Stronger than PMOS, then the switching threshold will be less than VDD by 2. And if the PMOS is what? Stronger than NMOS, then the switching threshold will be greater than VDD by 2. Okay. So let us now try to plot the voltage transfer characteristic in the 3 cases. Okay. VTC, it means what? The plot between V0 and Vin. Yes. Now for the first case where beta n is equal to what? Beta p, that is both the transistors being matched, the switching threshold, it is what? VDD by 2, and it is equal to what? 2.5 volts. And what is this switching threshold? It is the operating point or the point of intersection between V0 equal to Vin. Why V0 equal to Vin? Because of connecting this resistance between input and output of the inverter and the actual VTC of the inverter itself. Okay. So let this be the VTC in the first case. Okay. Let this be the VTC. So what is this value? It is VD. Even the ending value of Vin is what? VDD. Now because of connecting this RG, don't we get this what? Straight line V0 equal to Vin or Y equal to X, whose slope is what? 1. Whose slope is what? 1. And what is this point of intersection? Is it not Vm? That is what? The switching threshold, which is equal to 2.5 volts. Okay, is what? 2.5 is also 2.5. Okay, Now let us plot the voltage transfer characteristic for the second case where NMOS is what? 4 times stronger than PMOS, or beta N equal to 4 times beta P. In this case, the switching threshold has it not reduced from 2.5 to 2. That means what? The point of intersection between the straight line V naught equal to Vin and the voltage transfer characteristic is now 2 comma 2. Earlier it was what? 2.5 comma 2.5. Now it is what? 2 comma 2. Now where is this 2 comma 2? Will it be to the left of this or to the right of this? 2 comma 2, both x and y coordinates are what? Less than 2.5. That means what? That point of intersection would be to the left of this. See, will this straight line get shifted? No, right? As long as V naught is equal to Vn because of what? Connecting RG and so on, this straight line will remain the same. But the point of intersection, it is what? Definitely changing. That means what? The VTC will definitely shift either to the right or to the left. Let us say VTC are shifted to the right like this. Then the point of intersection, is it not to the right of 2.5? But in the second case, the point of intersection has to be left of this point. Whereas if the VTC gets shifted to the right, the point of intersection is also moving to the right, but that is not the case. That means what? The VTC has to get shifted to the left from its initial position. Only then the switching threshold also would move to the left of 2.5 comma 2.5. You understood? So how will the VTC get shifted when the NMOS becomes 4 times stronger than PMOS? Will it get shifted to the right or to the left? Like I just explained, it will get shifted to the left. You understood? Yes. I'll just clear this off. So the new voltage transfer characteristic for the second case, it would be something of this sort. The curve in blue color, and as you can see, this time the point of intersection is what? This thing between what two curves? Between the VTC and the straight line V naught equal to Vn. And this point of intersection is the new switching threshold of the CMOS inverter. Let me indicate the x and y coordinates of the new point of intersection. Are not 2 comma 2. And then in the third case, beta P is what? Greater than beta N, or PMOS is what? 4 times stronger than NMOS. And in this case, the switching threshold happens to be 3 volts. So what are the coordinates of the point of intersection now? Are they not 3 comma 3? Yes or no? The new coordinates of the switching threshold for the third case, they are what? 3 comma 3. This point is what? 2.5 comma 2.5. This point is what? 2 comma 2. So where will 3 comma 3 be? Will it not be to the right of this point? To the right of this point, it means what? This yellow color VTC should get shifted to the right. Only then even the point of intersection will get shifted to the right, such that the coordinates will be 3 comma 3. Okay. So for the what? Third case, where PMOS is what? Stronger than NMOS, the VTC will get shifted to the right. Okay. And this is the new point of intersection. And for this point of intersection also, there will be x and y coordinates, and there will be what? 3 comma 3. I hope you can make this out. Okay. So the middle yellow color VTC, that is for the 2 transistors being equally strong. The blue color VTC on the left side is what? For the case where NMOS is stronger than PMOS. And the red color VTC on the right side is what? For the case where PMOS is stronger than NMOS. Okay. So red color is for beta P greater than beta N. Yellow color is for beta N equal to beta P. And blue color is for beta N greater than beta P. Beta N greater than beta P. On the extreme right, it is for PMOS stronger than NMOS. Middle one is for PMOS equally strong as NMOS. And the blue color one on the extreme left is what? For NMOS being stronger than PMOS. Okay. So what is the conclusion here? If you make NMOS stronger than PMOS, if you make NMOS stronger than PMOS, then will the VTC get shifted to the right or to the left? NMOS, if you make it stronger than PMOS, then VTC will get shifted to the left. Or if you make PMOS stronger than NMOS, then VTC will get shifted to the right. Or I can also say, if you just increase the strength of the NMOS transistor, then VTC from its initial position will get shifted to the left. Or if you just increase the strength of the PMOS transistor, then VTC from its initial position will get shifted to the right. Make NMOS stronger than before, VTC gets shifted to the left. Make PMOS stronger than before, VTC will get shifted to the right. Always IP should be equal to what? IN. And for the two currents to be equal, the stronger transistor is always going to have a smaller overdrive voltage. That is how you decide whether the switching threshold will move to the right or to the left. Switching threshold moving to the right is same as what? VTC getting shifted to the right. Switching threshold moving to the left is what? Same as VTC getting shifted to the left. You understood? Yes. Now let's look at how the relative strength of the two transistors is related to the relative values of the two noise margins. Okay, what are the two noise margins? If you recall, in the last lecture, I had introduced the notion of noise margin, which is like the maximum noise that the logic gate can tolerate at its input without the input and output getting affected. Okay, there are two types of noise margins. One is what? NML, another is what? NMH. And what is this NML? I think it is VIL minus VOL, if I'm not wrong. NMH will be equal to what? I think VOH minus VIH. So NML is what? Noise margin for low input, and NMH is what? Noise margin for high input. Okay. Once again, let us say initially beta n equal to what? Beta p. That means what? In the CMOS inverter, both the transistors are matched. And if they are matched, what is the switching threshold? Will it not be VD by 2? Once again, let me draw the VTC. That is what? The plot between V0 and Vi. Okay. And in this case, where beta n is equal to what? Beta p, the VTC, let it be something like this. Let it be something like this. Again, this value is what? VD. This is also VD. Yes. Again, if you recall, the value of input where the slope of the VTC becomes minus 1, that is what? VIL. And it happens at 2 points on the VTC. So there will be what? VIL as well as VIH. Let us say at this point the slope becomes what? Minus 1. When I say slope, it is what? The slope of the tangent to the curve. Okay. And once again, let it be this point where the slope becomes minus 1. So what is this value? It is what? VIL. And what is this value? It is VIH. Okay. And is it not NML? And is it not NMH? Is it not NMH? Yes. And because the VTC is going to be symmetric. Why is it symmetric? Because only then the switching threshold is going to be exactly half of the supply voltage, or VD by 2. Okay. So when both are equally strong, VTC, it is what? Symmetric. VTC is what? Symmetric. Now, in the same CMOS inverter where initially both NMOS and PMOS are equally strong, let us make the PMOS stronger than NMOS. Initially, NMOS and PMOS are equally strong. VTC is what? Symmetric. So you would expect that the two noise margins are also going to be identical. So in this case, because of symmetry and so on, NML will be equal to what? NMH. Okay. Now in the same CMOS inverter, what are we doing? We are making the PMOS stronger than NMOS. Okay. Let us make PMOS stronger than NMOS. If you make the PMOS stronger than NMOS, then the switching threshold, will it be greater than or less than VD by 2? Like we found earlier, it will be greater than VD by 2. And because the switching threshold is what? Greater than VD by 2, the VTC will get shifted to the right. Yes. So the new VTC, when PMOS is made stronger than NMOS, let it be this thing. Let it be this thing. Okay. Once again, for the new VTC, there will be what? New values of VIL and VIH, okay? Look at this. Let this be the new VIL and let this be the new VIH, okay? Now, the new noise margin for low input, would it not be this thing? So, this is what? NML. And the new noise margin for high input, would it not be this thing? This is what? NMH. Just look at NML and NMH and tell me, are they identical or NML is greater than NMH? Because VTC is what? Getting shifted to the right. Obviously, NML becomes greater than NMH, okay? So, in this case, the two noise margins are no longer identical. The noise margin on the low side will be greater than the noise margin on the high side. NML will be greater than NMH. Now, what if you make NMOS stronger than PMOS? If you make NMOS stronger than PMOS, then the VTC from its yellow color position will get shifted to the left. VTC getting shifted to the left, it means what? NML would decrease, NMH would increase, okay? So, if you make NMOS stronger than PMOS, if you make NMOS stronger than PMOS, then the VTC will be something like this, okay? Now, this is what? NML, and this thing is what? NMH, okay? And clearly, NMH is going to be greater than NML, okay? So, both are equally strong, NML equal to NMH. PMOS stronger than NMOS, VTC will get shifted to the right. NML becomes greater than NMH. NMOS stronger than PMOS, VTC will get shifted to the left. NML will be less than NMH, okay?